comma y. Once we obtain the joint distribution, we can find the y hat, y estimate, y hat by computing the argmax for the joint probability distribution. This is the graphical view of HMM. For the example sentence, the dog bark. This is generated by the underlying hidden state sequence y1, y2, y3. This is these are directly these underlying hidden states can be directly mapped to the Watt tables. The main challenge here is we know the observation sequence, but we don't know the hidden states which generated this sequence. So during the inference problem, we have to estimate the most probable state sequence given the input sequence. In this example, the dog barks. The corresponding POS label sequence is y1 equal to determiner for the word the, and y2 equal to noun for the word dog, and y3 equal to verb for the word barks. Let's discuss on how to generate a sentence using HMM. From the start state, we can visit any of the other states. Either it can be determiner or noun or verb, and emit the observation word, the dog or barks in the vocabulary, and then transition to the other state, either noun or verb, or do a self transition from the same state, self transition to the same state. This is how we can generate a sentence using HMM in a generative way. Let's establish some notation. Let's say V is the set of all words in the language. In general, this will be in the order of millions, and S be the set of all states or tags, and S can be determiner, noun, verb, and all possible POS tags, and much more fine-grained categories can also come in. And let X be the sentence in the language, and X1, X2, X3, X4 up to so on, Xn represents the words, and Y represent the states of the labels. Let's consider a simple example, the dog barks, and let's see what are the parameters involved in modeling using HMM. These are the values which we had provided as a sake of example for understanding. From the start state, let's say in the start state, we can visit any of the three states, determiner, noun, or a verb. So the initial transition probability is captured by initial probabilities, which is denoted as a pi. And after reaching to any of these states, we can transition to other state, noun or a verb. These are captured using transition probabilities a yt minus 1 comma yt, where this rows indicates the previous state yt minus 1, and the columns indicates the current state yt. For this example, a det comma noun indicates the transitioning from determiner state to noun state, which is indicated here, and transitioning from noun to verb. Is indicated here, and after reaching a state, HMM emits a observation word, which emits out of the vocabulary which we consider. In this particular, the vocabulary is the dog barks. So the probability of emitting the word the in the determiner state is given by 0.04, which is indicated here, and the probability of emitting the word barks from the noun state is 0.031, which is indicated here. So these are the parameters involved in HMM. Let's define it more formally. The initial probability of starting from a state Si is indicated using pi Si, and the transition probabilities, probability of transitioning from state SL to state SM is indicated by ASL and the probability of emitting a word Vk at state Sj is indicated by B Sj comma Vi. Sorry, this is a typo here. This is Vk. In hidden Markov models, we want to model the joint distribution of observation and the hidden state sequence. So we can express this joint distribution in terms of initial probabilities and the transition probabilities. The factorization for this factorization we made two assumptions. One is the Markovian process. A state is conditionally independent of all other states given the previous state, which means that probability of yt given yt minus 1 is conditionally independent of all other previous states. And one more assumption is observation independence. The output observation xt depends only on the state that produces the observation, which is indicated by probability of xt given yt. Given the yt, the xt is conditionally independent of all the previous observation yt, all the previous states yt minus 1 to y1 and all the previous observation xt minus x1. So this is observation independence. Since in HMM we only know the observation sequence and the underlying hidden state sequence is unknown, we have to, in order to compute the likelihood over the data, we have to summate over all possible hidden state sequences. So this is obtained by marginalizing over the state sequence. With this background on the HMM, let's see the three problems we want to address in HMMs. First one is the inference problem. Given an observation sequence and an HMM, determine the most possible hidden state sequence. And in the likelihood problem, determine the overall likelihood of an observation sequence X being generated by the HMM. While in the training, we have to find the best parameters for HMM for the given data. Let's first discuss about the inference problem. Let's understand the inference problem using the POS sequential learning problem and consider the example, the dog barks. Given this sequence, we have to find the underlying hidden state sequence which generated this sequence. This is the trellis diagram of HMM where the states are indicated here, and while going from left to right, this indicates the instance of sequence 1, 2, and 3. For the given sentence dog barks, we have to find the best possible sequence state it generated. To do it efficiently in HMMs, we have to do this one efficiently in the HMMs. If we do in a brute force way, there are like 27 possible sequences, paths are possible. Since there are 3 states and the sequence length is n, there are 27 possible possible paths are possible. So in order to do it efficiently, what we use in HMM is the Viterbi decoding, which is popularly known as a dynamic programming. So in order to compute, in order to perform the inference, first let's define deltas here. The initial delta, delta S of 1 is the probability of starting in the state S and emitting the symbol x1 in the first position. This is indicated by, this is computed by initial probability and emission probability of being in a state S and emitting the word x1. So this is how the deltas are computed in the first instance, and In the subsequent instances, we can make use of recursive solution to compute this. This is possible because of the Markovian assumption we made, where uh, the current state is independent only on the previous state, and the current state is dependent only on the previous state and independent on all the previous other states. So by making use of the Markovian assumption, we can rewrite deltas in terms of previous deltas, and the transition probabilities from that particular state to the current state, and also the emission probability of being in the state SM and emitting the symbol XT. And in order to decode the sequence, best possible sequence, similar to the backtracking pointer in dynamic programming, here we use sigma to backtrack the best possible state sequence, which is the argmax or SL, which keeps track of what is the best possible previous state. Let's try to understand this with an example. Let's try to decode the hidden state for the example which we considered, the dog barks. Let's say if you want to compute delta for the delta 2 at the second sequence instance, and for the word dog, delta noun of 2, which is indicated by delta noun of 2, represents the probability of reaching the state noun and emitting the symbol dog. And we need to find what is the best possible path out of these 3 to reach this particular state. In order to compute that, first let's see the possibility of coming from determiner state, and in that state emitting the symbol the. So this is computed by pi det into multiplied by emission probability of the word the being in the state determiner. And in order to compute the path, we have to multiply with the transition probability. After multiplying with the transition probability, and then reaching the state noun and emitting the symbol dog, which is indicated by emission probability of b noun comma dog. This is the first term, and we have to compute all possible paths. So the other possibility is reaching from the state noun to noun by and while in the previous state emitting the symbol the. So this is represented by this particular term, being in the state, the initial probability, the previous delta noun into transition probability and the emission probability here. Similarly, we can compute the path associated with verb to noun using this equation. So out of these 3, we have to find the best possible path. So let's consider the previous values and substitute the values here. So these are the values. Recall that the observation, the emission probability of the word the being in the state noun is 0, and also the emission probability of the word the being in the state verb is also 0. So in this expression, these 2 terms will become 0, and the argmax of the previous term in the backtracking variable will goes to determiner, since the observation probabilities of these 2 terms are 0. Similarly, we have to compute the deltas for all possible states in all sequences using the recursive approach. And after reaching the final instance of the sequence, we can find the argmax of the deltas which we computed. In this case, it turns out that the last tag, which is the most likely tag, is a verb, and and after obtaining this, try to find what is the previous best path, and going further backward, we can decode the whole possible state sequence. So this is the inference algorithm in Viterbi. This is similar to what you might have already familiar with the dynamic programming. And the second problem is the likelihood computation problem. Here, the goal is to determine the likelihood of the data, p theta of x1 given up to so on, given the observation sequence x1 to xn. Since we don't know the likelihood, since we don't have access to the hidden states, we have to marginalize it over all possible hidden state sequence. Summing over all possible state sequence could result in computationally expensive. So let's consider the HMM with n states and length of observation is t. Let's consider this case. In this case, the possible number of computations involved here is order of t into n power t. By making use of the Markovian assumption, we do not have to explicitly compute each possible path, but we can make use of Markovian assumption and then do it efficiently. This one such algorithm is forward algorithm, which results in a reduction in the computational accuracy, which is of order of t n square. Let's see what is forward algorithm. In forward algorithm, the probability of observing the observation sequence x1 to xt and being in the state s at time t is given by alpha s of t, which is the probability of observing the sequence x1 to xt, and the hidden and at the tth instant the hidden state is s. Let's initialize this alphas in the first state as the probability of starting the state sequence with a particular state s is is computed as initial probability of being in that state s and emitting the symbol x1. In emitting the symbol x1, probability of emitting the symbol x1 in the state s. This is similar to what we have seen in what we have observed in computing the inference problem using deltas. Similarly for alpha s of t, from the initial state to the successive states, we can make use of the recursive solution, recursive approach by the previous alphas and then compute it efficiently rather than enumerating each sequence. Compute the probabilities recursively using the Markovian assumption. That's the idea here. This is pretty similar to the deltas which you computed in inference algorithm, but the only change is that there we use the max operator to obtain the best possible path, while here we perform summation to marginalize over all possible state sequences. And the likelihood of the data is computed by computing the alphas of the final sequence instance and then summing it over all possible states. Similar to the forward probabilities, we can compute the backward probabilities using betas. These are further used in HMM training to find the parameters. To estimate the state occupancy probabilities, betas are utilized over there. We can see it in the later part. So let's try to define the beta and then try to understand how we can also compute the likelihood using beta. The beta indicates the probability of future observations given that HMM is in state S at time t. Similar to forward probabilities, we can also compute backward probabilities, starting from the backwards and then coming towards the left side. So we can initialize it with beta s of t, which indicates the final probability, which is equal to 1, and then let's integrate the and then for beta t minus 1 is computed recursively using future betas and the transition probabilities and the observations in the future states. We can also compute likelihood using the backward probabilities using this equation, which is a summation over all possible betas in the initial state and the initial state probability matrix, probability values, and the corresponding emission probabilities. So far we discussed about inference and likelihood problem, and next we will discuss about the training HMM using training HMM parameters and obtain the parameters of the HMM. Based upon the availability of the labeled data, we can train HMM in two approaches. If the entire training data is labeled, then we can perform supervised training. But when the huge amount of data is unlabeled, then we have to go for semi-supervised modeling. Let's first consider the supervised approach. In supervised training, we have access to the labeled data. So the input sequence is associated with the corresponding state sequence. Recall that joint distribution is expressed in the form of mark in this form by factorizing it in terms of initial probability and transition probabilities and then emission probabilities. We can rewrite this expression since the labeled data is available. We can rewrite this expression in terms of model parameters. If we rewrite this expression, these are the initial probabilities, and p of x given p of y given yt given yt minus 1 is the transition probabilities, which are represented by A's. ASL, SM indicates the state transition from SL to SM, and CA, SL, SM indicates the number of transition from state SL to SM, and BJs are the emission probabilities, and CB indicates the number of emissions of the word VK from the state SJ. So for simplicity, ignore this term and try to estimate the parameters of A's and B's and considering this term. Recall that A's and B's are the transition and emission probabilities, and these and they should sum up to 1. So for each SL, the transition probabilities summing over all possible reachable future states should sum up to 1, and similarly within each state, the emission probabilities summation over all possible watts should sum up to 1. So these are the constraints used to solve the objective function. So for each state, different optimization functions are defined for both transition and emission parameters. For transition parameters, this is the objective function, log of the product of the terms involved with transition parameters and the corresponding counts using the constraint over the transition parameters. And similarly, for emission parameters, we can define the objective function and the constraint over the transition over the emission parameters. So these are solved using Lagrange multipliers. So using the Lagrange multipliers, we can introduce the Lagrange variable and then uh, and try to maximize this particular objective function for transition parameters, and the corresponding expression for the emission parameters is this one. So these are the parameters of A's and betas can be obtained by differentiating and equating these objective functions to zero. We can differentiating the terms and equating to zero will give us this one. In this objective function, we have to differentiate with respect to A, SL, comma SM, which are the transition parameters which we are interested to estimate. So in this particular summation, there is only one term which will be dependent on ASL, comma SM. Similarly here, so differentiating with respect to the ASL, comma SM will result in CA divided by ASL, comma SM plus this factor. This turns out to be lambda A. So these are the expressions. These are the expressions for the solution for transition and emission parameters. While lambda A and lambda B are the Lagrange multiplier parameters which are unknown. Let's try to estimate these parameters. Rearranging the terms by moving the lambda to RHS and then summing it over all possible states. We know this term is 1, and which implies that lambda equal to summation over Sm of the counts of this equation. Similarly, for rearranging the terms and solving for lambda b results in this expression. Once we get the lambdas, we can go back and substitute in this equation to find the transition parameters and beta parameters. So these are the expressions. These are the final estimate of the parameters by solving the Lagrange, by solving the objective function using Lagrange multipliers using the constraints. We arrive at these estimates for transition and emission parameters. Let's understand what this mean in terms of words. So the transition parameters A theta SL comma SM indicates the number of transitions from state SL to SM divided by the total number of counts of state SL. Similarly, the probability of emitting a word Vk from state SA is given by B SA comma Vk, which are number of emissions from the word Vk from the state SA, and the number of total counts of state SA. And these are fairly intuitive. Yeah. These are the solutions we arrive at for supervised learning. Let's see how to do for semi-supervised learning. Let's say some data is labeled. Then we can estimate the initial estimate using the supervised approach, and from the unlabeled data, we can use EM algorithm to estimate the maximum likelihood of unlabeled data. By this is an iterative approach. Direct optimization is not possible as the state sequence is hidden, which leads to some overall possible state sequence. And so in order to address this problem, we use EM approach to iteratively estimate the parameters, which maximizes the likelihood of the data. In EM, in order to solve using EM, we have to define an auxiliary function. In this case, it's an expectation over the hidden sequences, hidden state sequences over the joint distribution, where the observations are known and the state sequences are hidden and unknown. In each iteration, we have an expectation step and a maximization step. In expectation step, each step, we compute the expectation over hidden sequences given the current parameter theta I. And once we compute the expectation of this parameter of this expression in the nth step, uh, given the current parameter theta I, we need to estimate theta I plus 1 by maximizing the log likelihood, which maximizes this expression. So that is the theta I plus 1 for on every iteration, from iteration to iteration. The likelihood of the data will keep increasing. Will stop the iterations when the likelihood saturates. So by rewriting the expressions which of the joint distribution in terms of initial probabilities and transition probabilities and emission probabilities, by applying the log, we arrive at this equation. So we also know that expectation is a linear operator. Expectation of sum is equal to sum of expectations. So we can split this expression in terms of in order to compute for each parameter separately, 3 parameters. First one is initial probabilities, and the transition probabilities and the emission probabilities. We can compute the 3 objectives separately. So this is the objective function 1, 2, and 3. Let's first consider the objective function 1 and optimize it and find the parameter and find the estimate for initial probabilities. First, we have to compute the expectation over the hidden sequence. So expressing this expectation in terms of summation over the conditional distribution, and writing, we can rewrite it in terms of posterior and the model parameters. Let's see how to compute this posterior, and then we'll come back to this particular expression and substitute it. The posterior p theta I of y being in the state s given the observation sequence is proportional to the joint distribution, and we can rearrange the terms here, and then remember we defined alpha and beta parameters as forward and backward probabilities. So we can make use of the back forward and backward probabilities, and then express this term in terms of alphas and betas. This is remember this is a proportionality. So in order to, and this is a probability parameter, probability value. So in order to get convert this one into probabilities, we have to normalize with a normalizing constant by summing over all possible state sequence. So once we obtain the posterior, we can go back and substitute it in this expression. In the similar fashion, which we did for supervised learning, the initial parameters are probabilities, and the estimate should sum up to 1. So we introduce the Lagrangian and Lagrangian multiplier, and then rewrite the objective function in this form. We follow the similar steps, differentiating with respect to the parameter we are interested in and equating to 0, and then find the estimate for the Lagrangian, and find the and we can find the estimate for the initial probabilities. So this probability is so initial the estimate is given by alpha 1 of s times beta 1 of s divided by the normalizing constant. What does it mean is this indicates the expected frequency being of state s at the time t1. Similar approach is carried out for the objective function 2 to estimate the parameters of transition probabilities, computing the conditional expectation and factorizing, computing the conditional expectation and factorizing it in terms of posterior and model parameters. Let's see what the posterior in this case looks like. Similar to what we did earlier, the posterior can be represented in terms of joint distribution and then factorizing it in terms of forward and backward probabilities. We arrive at this equation, and similarly, if you normalize it, we can go back and substitute this posterior in this expression, and introduce the Lagrangian multiplier, and differentiating and solving it, we get this particular estimate, which indicates that expected number of transitions from state SL to SM divided by expected number of transitions from state SL. This is similar. The solution is similar to the solution we arrived during supervised approach, where we have the number of transitions from state SL to SM. Since the data, in unsupervised learning we don't have access to the labeled data, what we observed, what we did here is to estimate it and approximate using the soft labels. That's the difference from supervised to unsupervised approach. Similarly, we can estimate the emission probabilities by solving the objective function 3. We can estimate the emission probabilities in terms of gamma, and I here indicates the indicator variable, indicator function, which takes 1 when the observation xt equal to vk, what vk, where gamma t indicate gamma SL of t is the probability of being in state SL at time t given the entire observation sequence. So in terms of words, we can express this expression as expected number of times in state SL and observing the symbol Vk divided by expected number of times in state SL. These are the estimates for B in unsupervised learning. Sorry, semi-supervised learning. So far, this is about estimating the parameters in HMM training using supervised and semi-supervised approach. We considered the example of POS problem, parts of speech tagging problem. We can also apply the similar approaches for in speech applications. The same modeling approach holds for applications in speech like automatic speech recognition and text-to-speech synthesis. The difference is that in POS tagging problem, the observations are in discrete space, and it is modeled using probability mass function. While in ASR or speech applications, the observations are in continuous space. Let's say given a speech signal, it is first segmented into short windows of duration 20 to 30 milliseconds with an overlap of 10 milliseconds in successive frames, and extract spectral features. These are used as a feature sequence x1 to xn. Given an acoustic sequence as an input, the acoustic model is modeled using HMM, and given the acoustic sequence, it estimates the best possible phone sequence. And since the observations are continuous space, unlike in POS tagging problem where we consider probability mass function, in the case of speech applications, we consider emission probabilities as a continuous densities, and this can be modeled using Gaussian mixture models. That's about speech applications. Let's recap what we discussed so far. First, we considered a simple example of using of POS problem, and we formulated it in terms of sequence learning problem and model using HMM. And then we discussed about the problems involved in HMM, inference problem. In inference problem, we used delta. We defined delta parameters, and using dynamic programming, which is also known as Viterbi algorithm, we performed inference efficiently. And also we discussed about forward algorithm to compute the likelihood of the data. using forward and backward probabilities. And finally, we discussed two approaches to estimate the parameters when depending upon the availability of the data, labeled data, in supervised and semi-supervised approaches. On a final note, HMMs are classical models which are used to solve the sequence learning problems. Recently, there are more advanced methods using neural network-based approaches to address these sequential learning problems. In the next part of this session, Pritham will cover attention and bed-based model to address these sequential learning problems. Thank you.